Hi, my name is Dr. Tishan. In this video, we're going to find the area between curves. If you recall from your geometry class, when you computed area of geometric shapes, we would find the area of a circle using the formula pi times radius squared, and we'd find the area of a rectangle using length times width. Well, what if the shape that you want to find the area of is an irregular shape? And it's not a rectangle, it's not a circle. What if it's an irregular shape? Well, we're going to need to use integral calculus to figure out the area of irregular shapes. So we first need to generate the irregular shape, and we're generating that by using two functions, okay? And we're going to put two functions on a graph, and we're going to figure out how to find the area bounded between the two curves that are given to us. So let's take a quick look at the formula, and then we'll look at an example to see how it works. So to find the area between two curves, we want to take our two curves, and we want to just take one of the functions and subtract the other, so we want to subtract the functions. But when you do set up the subtraction of functions, you want to make sure you're taking the function with the larger values, and you want to subtract from that the function with the smaller values. So we're going to integrate from a to b, function of x minus function of g, and this is providing that the values on the f function are greater than or equal to the values on the g function. So whichever function has the greater values, that's one that comes first, and we subtract the smaller values from it. And then that'll keep you from having a negative answer. So for an example, we want to take our f of x, and we're going to call that x squared, and our g of x is 4x minus x squared. And we want to start by sketching. We want a nice sketch of this graph so we can see what's going on here, okay? So here's my x-axis, here's my y-axis, and we want to graph this. So f of x equals x. Well, it's a parabola that opens up, sits on the origin. And then here's a parabola that opens down. It's going to be shifted over a little bit with the, let's see, the x-intercepts at 0 and 4. But I mean, if you're not sure what they look, what they look like, you can always use technology if you're allowed to do that. But use some technology to get a picture of the graph. I'm going to use the TI-89, the Texas Instrument 89, just to show the technology with these topics. So if you grab your TI-89, and you turn the TI-89 on and hit the home button. Once you hit the home button, you're at this screen right here. And we want to go ahead and figure out what the graph of this looks like. So we want to get to the graphing screen. So you're going to need to go to the y equals. Y equals is up here on top of the F1 button in green. So you have to hit this green diamond key, and then you hit the F1, and that gets you to your y equals screen so you can put the functions in. So the first function we want to put in is x raised to the second power. So you're going to hit x raised to the second. You don't have its squared key on here, so you got to hit the actual raised to the second power, and then you hit enter, so it'll drop it into place, and there's your x squared. And then the other function we have over here, 4x minus x squared for the g function, we'll put that in y2. So y2, just start typing 4 times x, okay, minus x raised to the second power, hit enter, and that gets dropped into the y2. So you can see y1 is x squared and y2 4x minus x squared, and we have that. We want to know what this function looks like, and you could use their standard windows built in. So if you hit the zoom, if you hit the F2 up here on the top of the screen, you can see if you hit the F2 button, it gives you a zoom window. So if you hit the F2, you have so many choices of windows here. Number 6 is number 6, zoom number 6, the standard zoom window. Standard gives you a -10 to 10 for the x, -10 to 10 for the y. So you can choose a zoom and choose number 6, and it gives you a -10 to 10, -10 to 10 window. There's your parabola opens up, there's your parabola that opens down. And so if you can, looking at this, the window -10 to 10, well, that might not be the best window for this. You might want to pick a better window so you can see your curves a little bit better. So how would you actually do that if you wanted to put your own window in? You can actually put your own window. Take a look at this graph right here. I want the area of the region overlapped right between these two curves. I'm going to give myself a better window. I do not need all these negative x's, okay, and I don't need all these negative y's, so I'm going to go ahead and give myself a better window. And so you can see where it says window on top of the F2 button, hit your green diamond, and then hit that F2 button, and it allows you to put your own window in. As you can see, we have the -10 to 10 for the x min, x max, and then y min, y max, -10 to 10. But let's change it up a little bit. Instead of -10, let's maybe go -5. For the x min, okay, maybe -5 to 5. Let's see what that's going to do, okay? And then the y minimum, let's do -5 and go to -5 to 5 for the y min, y max, okay? So let's do that for a window, try that one. So, and then green diamond, your F3 key, okay? And then, so this gives us a better picture. There's the parabola opens up, and here is the parabola opens down. You can see it a little bit better. So when you're graphing on the TI-89, that green diamond F1, put the functions in, okay? Green diamond F2 will set up a window so you can get a good idea of what the area you need. And then green diamond F3, and that's where your graph is, okay? So this is how you would use the technology to set up, to see what your graph looks like. So let's go ahead and sketch this on the board. So we'll sketch this over here, and I'll color code this, all right? So I'm going to take the parabola that opens up. I'm going to take the f of x equals x squared, and let's go ahead and draw that parabola. There's the parabola opens up, and I just really need it in the first quadrant, right? Okay. And then let's go ahead and take the f of x minus x squared, okay? And I'll use the green color for that, so we'll put a green. This is the parabola. It goes through the origin, doesn't it? Okay, and that comes up and it opens down, all right? So I have my blue parabola, my f function's in blue, the parabola opens up, and my green function is the parabola that opens down. And you can see that this is what I want the area. I want to find the area of this region right here. And it's not a circle, it's not a rectangle, it's not a triangle, it's an irregular shape. So we need integral calculus to compute this area. So we want to set up, this is just an integral expression that involves both our functions. So let's go ahead and write the area equation. All right, so to compute the area between these two curves, we're going to set up a definite integral, and we're going to take our one function and we're going to subtract our other function from it, okay? Now, which order do we put the functions in that we want to subtract? So if you're looking at your shaded region, look at the shaded region, the first function has to be the function with the greater values, like the curve that's sitting on top, okay? The higher curve on the y-axis is the one with the greater values. So which curve here has the greater values? Which curve? Look at the shade region. Which curve is sitting on top? That's definitely the parabola that opens down. So that is actually my g function, the 4x minus x squared. Try to color code this with the curve. Okay, so it's that function there. All right, and then what goes here? Well, that's going to be my, look at the region here. It's going to be the function in this scenario with the smaller values, okay? So the function that's sitting where my shaded region is, it's the bottom curve. It's the one sitting below, which is the parabola that opens up, which is x squared, okay? So here's your setup, all right? So you pretty much want to take like the top curve and subtract out the bottom curve is what you want to do, all right? So, and then if you remember the concept, when you integrate a function by itself, it gives you the area of that function to the x-axis. So we're getting the area the parabola opens down by itself, that's the area to the x-axis, but then we're going to subtract the area under the curve of the parabola opens up. So when you're taking the area under the curve of the parabola opens down and subtracting the area under the curve of the parabola opens up, you got the shaded region left over. And you want to make sure that you're subtracting the region with the greater values, okay? Because the bigger minus a smaller is going to give you a positive answer. All right, so now we have the integrand all set up, okay? We have the integrand all set up. We need the bounds of integration. And how do we find the bounds of integration? The bounds of integration are going to be the x-coordinates of your points of intersection, okay? So to get the bounds of integration, we need the points of intersection. To find the points of intersection, you're going to take these two curves and set them equal to each other. You're going to take x squared and set it equal to 4x minus x squared. You're going to set the curves equal. All right, and then algebraically solve. So it's a quadratic, so move all the terms to the left, add x squared to both sides, so 2x squared, subtract 4x, okay? Because it's a quadratic, all the terms to the left, 0 on the right, and then we're going to see how we can factor this. Looks like we can factor out at 2x, factor out at 2x, and so you end up with x is 2 and x is 0. All right, let me put them in order though. X is 0 over here, right, and x is 2. All right, so those are the solutions to our solving the quadratic. Those are the x-coordinates of the points of intersection, which means those will be our bounds of integration from 0 to 2. All right, so now we have our definite integral all set up that'll give us the area of this shape. All we need to do now is compute this integral. And so you've probably done plenty of computing integration by hand, but let's go ahead and see how this is done on the TI-89. All right, so let's actually do the numerical integration on the TI-89, back to the TI-89, and I still have the graphs up, so let's go ahead and hit the home button, okay? And I'm using the TI-89, again, graphing calculator. Let's hit the home button, All right, and so we're at the home screen, and we want to choose, go to the F3. If you look at F3 up above there, that is your calculus menu, okay? So you're going to hit the F3 button, all right? Hit the F3 button, and we're going to choose number 2, integration. We want to integrate. Choose number 2. Now the parameters, okay, you have to type in the functions in the integrand, okay, comma, variable, comma, lower bound, comma, upper bound. There's 4 things you got to type in here, all right? Let's start with the integrand. The integrand is what? The parabola that opens down minus the parabola that opens up. So I'm going to put parentheses. It's going to be 4x minus x raised to the 2nd power, all right, minus the parabola opens up, which is x squared. Okay, so there's your, so you have the, so the parabola opens up, there's your integrand, 4x minus x squared minus x squared, okay? Then you have to put a comma, put the variable x, comma, lower bound is 0, comma, upper bound 2, close parenthesis, all right? Anytime you do numeric integration, you want them to compute the area under a curve or volume, whatever you're working on, you're going to choose F3, the math menu, okay, the calculus menu, F3, choose number 2, integrate. 4 things to type in, 4 things in the parameter. You got to type in the expression, comma variable, comma lower bound, comma upper bound, close parenthesis, and hit enter. All right, so when you do hit enter, there's a pretty print feature in here. Before you take the answer, take a look and make sure it says exactly what it needs to say. All right, we want to integrate from 0 to 2. We wanted to take the 4x minus x squared first and subtract the x squared, okay, with respect to x, okay, and then we have all that so we can take the answer. It says 8/3, and so the answer is 8/3. All right, so that's what this area would be. All right, so this area is 8/3, and we're done with this problem. All right, so here's area between 2 curves. We sketch our diagram, write our equation carefully, and then our answer. Okay, so make sure, keep in mind that this is not going to be literally f of x minus g of x, right? Okay, because this here, my f curve was x squared, but my x squared went in the g, that position, okay? So it's providing that the values on the f are greater than the values on the g, okay? So if the values on the g are greater than the values on the f, then that's what you have to put first, all right? Okay, so that's what you would have to put first, because you have to take the larger values and take away the smaller values, so you don't want to get a negative area, all right? So let's take a look at the example over here. What if you're given an equation with y's in it in terms of y? So how would we handle this? Okay, so now instead of having a vertical representation, pretty much like we did the top curve minus the bottom curve, this is going to give us more of a horizontal representation. All right, so it's a horizontal representation. We're going to need to sketch the curve first. All right, a little bit trickier maybe to sketch the curve because sometimes your, technology is not going to help you as much. All right, sometimes f of y and g of y, they're not necessarily always going to be functions. All right, so if they're not functions, then you're going to have a tough time graphing them with your calculator. Okay, so I mean we have functions over here. Like for example, you're probably used to seeing that y is f of x. Okay, so you've written. So when your functions in terms of x, y and f of x are the same thing. Okay, what if they're going to call it f of y? Okay, so f of y, and this is my cursive letter f. Okay, so so what if they call it f of y? Well, that's x, isn't it? Okay, all right. Function of x, well that's y. Y and f of x, same thing. But function in terms of y, that's x equals. All right. So we can take these, just like you can write this as y equals x squared. You can write these as y equals. Well, over here, this would be x equals y squared. Okay. So you can write that. So in other words, f of y equals y squared is the same thing as x equals y squared. It's the same thing. All right. So you can write it like this. Okay. This graph down here is the same thing as x equals y plus 2 because you're writing in terms of y. It's the same thing. All right. And how do you graph x equals y squared? How do we graph that? Okay, all right, because we know, so y equals x squared, we know that's a parabola that sits on the origin, opens up. And y equals a negative x squared, okay, that's a parabola that just kind of sits on the origin but opens down. What if it's x equals y squared? It's still a parabola, all right, but it's not going to be a function anymore, is it? All right, still a parabola, just it's a parabola that opens to the right, okay? And if you had x equals negative y squared by any chance, okay, well that's your parabola. It's from the origin, sits on the origin, but opens to the left, right? So we're dealing with x equals y squared. F of y is y squared, and we need to go ahead and graph that. All right, so let me just go ahead over here and graph that. So f equals y squared is a parabola that opens to the right. Okay, so when you don't have, when it's not a function. So, you know, the graphing calculators are in function mode. They graph functions. When it's not a function, and if you're going to try to put it in, you have to put it in more than one piece. So handy to try to know what these look like. And then what about this? This is just the equation of a line. Okay, so if you want to see it in slope-intercept form, all you have to do is subtract 2 from both sides. So y is equal to x minus 2. There's your slope-intercept form. All right. So subtract 2 from both sides, y equals mx plus b form. Your slope is, your y-intercept is a negative 2 and your slope is a positive 1. So you're dealing with a curve looking something like this. All right. So what do we want to do with this? We want the area, and we want to find the area, and it's an irregular shape again. Okay? It's not a circle, not a square, not a triangle, so we're going to have to set up a definite integral to get the area of the, when I shaded in red. We want to find the area. All right, so we want to find the area between these two curves. So we're going to set up a definite integral, all right, and we are going to subtract one curve from the other curve, and this is going to be in terms of y, all right. So we want to figure out which way to work this, all right. So you have to take the greater values and you have to subtract the smaller values. So f of y minus g of y, providing that the f of y values are greater. So when you're dealing with f of y, okay, just like over here in terms of x, top minus bottom, these values up here are bigger than the values down here, top minus bottom. Well, what do you do if it's horizontal along the x-axis? Where are the values greater? The values are greater over here. You got to take the right side minus the left side. You got to take the greater values and subtract the smaller values. So when you set up your definite integral to find the area of this region here, you got to take the curve that's on the right hand side, because that's where the greater values are. You got to take the curve on the right hand side, which is the line which is y plus 2. All right, and you have to subtract from that the curve that's on the left hand side. Okay, so it's right minus left essentially. The curve on the left hand side is the y squared. All right, and we're writing everything in terms of y. In terms of y, the curves are given to us in terms of y, not in terms of x. All right. So when you're finding the area in terms of x, top minus bottom. Top minus bottom is how you get the bigger values minus the smaller. When you're doing the area in terms of y, it's going to be the curve on the right minus the curve on the left. That's because the bigger values minus the smaller values. All right. Bounds of integration. The bounds of integration will be the points of intersection. To find the bounds of integration, you need to get the points of intersection. So points of intersection, set the curves equal to each other. Set y squared equal to y plus 2. Set the curves equal and solve for y. This will be in terms of y. The curves are in terms of y. It's a quadratic again also. So you want to move all the terms to the left hand side. So y squared. Okay, minus y minus 2 and a 0 on the left. Okay, so when you solve a quadratic, all terms to the left and a 0 on the right. Okay, and this is factorable. This is what? This is y minus 2 times y plus 1. All right, so y equals positive 2 and y equals a negative 1. Okay, so those would be the bounds of integration. So the bounds of integration are going to be the points of intersection, like the y coordinates in this case. So it's going to go from negative 1, right, to 2, negative 1 to 2. So, and there's your setup. There's a setup, and then we'll use it. Let's use the technology. Let's use the technology to compute this area. All right, so we'll use the TI-89 to compute the area. All right, so grabbing the TI-89, I'm going to clear out the last problem. All right, and back to the home screen, just to the home screen, and let's do this numeric integration. So take a look on the board again. So we want to integrate from negative 1 to 2. The line y plus 2 minus y squared, okay? So on your calculators, all right, so we're going to go to, at the home screen, calculus menus, F3. Okay, choose number 2. We want to integrate. And we're going to integrate, and I'm going to put parenthesis y plus 2. I'm going to use y, all right, because it's y, all right, minus, and I'm going to put parenthesis y raised to the second power. I'm going to take my larger function minus my smaller function. With respect to y, lower bound is negative 1, upper bound is a positive 2. Make sure you distinguish between the negative sign on a number and a subtraction operation, okay? And so this is typed in, and let's see if we got it typed in properly. So you want to look and make sure that pretty print there. So did we type in from -1 to 2, okay? And then y plus 2 minus y squared. Make sure you typed it in right before you go and take the answer, which the answer is 9/2. All right, so the area bounded between these two curves is 9/2, and there we have it. All right, so area between curves. If it's a circle or a square or a triangle, we just use geometry formulas, right? But if it's an irregular shape, that's where calculus comes in. We find area and volume of irregular shapes. So if they're going to give you equations in terms of x, just graph it carefully, get a nice picture so you can see what you're doing, and you're going to take pretty much a top curve minus the bottom curve. You want to take the curve with the bigger values and subtract out the curve with the smaller values to compute your area. All right, and if they give you in terms of y, well, it's just the right minus the left because you have a horizontal representation. You want to take the bigger values minus the smaller values in that direction. So, okay, that is it. I hope this helps. Thank you for tuning in, and I appreciate it. Take care.